Suppose we have a finite dimensional subspace S of an inner product space V. So for example, S can be the xy plane and V is 3 space. And if we have a vector B in the vector space V, then a projection of B on S is the closest approximation to B from S. So this can be seen geometrically by projecting B onto the subspace S. So we have an orthogonal projection, and this red vector, which we'll call S1, is the best approximation. So in other words, if we subtract S1 from B, where S1 is the orthogonal projection of B on S, so that'll give this vector over here, and we take the magnitude of this vector to be the error in the approximation. So in other words, if B was somewhere here, then this error would be smaller. And this error is always less than the norm of the vector B minus a vector S from the subspace S for every vector S in the subspace S, other than the projection of B onto S. So this can be visualized if we look at the vector S2, for example, and then this vector here is B minus S2, and if you take the norm of this vector, you can see that it's larger than the norm of this vector here, which is a component of B that's orthogonal to the projected vector on the subspace. And we're going to use this idea to get an approximation to the solution of a linear system that may have no solution at all. So the system may be inconsistent. Suppose we have a linear system, Ax equals B. So this has P equations and Q unknowns, with the matrix A being a P by Q matrix. And this system may be inconsistent, so it may not have a solution. So the least squares approximation involves finding a vector x that minimizes the norm of B minus Ax, and this x is called the least squares solution of this system. And B minus Ax is the least squares error vector. So this error vector has P components equal to the number of equations. And the least squares error is equal to the norm of E. So the goal of the least squares approximation is to minimize this error, and x is called the least squares solution because minimizing this error also minimizes the square of the error. Let's look at one possible method for finding the least squares solution for a linear system Ax equals B. So remember that multiplying A by x results in a vector that's in the column space of A, because we're effectively multiplying each component of x by each column of A. So in other words, that's equal to the projection of some vector B that may not be in the column space of A onto the column space of A. And we can calculate this projection using the dot product between B and the column vectors of A, but to avoid doing that, we can subtract the terms on both sides from the vector B. So we'll have B minus the orthogonal projection of B onto the column space of A. So given that this is the component of the vector B that's orthogonal to the column space of A, then this vector lies in the null space of the transpose of A. So remember that these fundamental matrix spaces that we covered are orthogonal complements of each other. So this means that this vector on the right hand side is in the solution space of the homogeneous linear system corresponding to A transpose. So we have the transpose of A by B minus a projection of B onto the column space of A is equal to 0. And this means that the transpose multiplied by B minus AX is equal to 0. And then solving this equation, we obtain A transpose by A by X is equal to A transpose by B. So this is called the normal system associated with this linear system. And from this, you can solve for X by multiplying both sides by the inverse of the matrix on the left hand side, and then we have AT by B. But you'd normally use Gaussian elimination where A is large and there's no unique solution, where the inverse does not exist. And the error in this approximation to B can be obtained by taking the norm of B minus AX. So for example, given this matrix A, we can first calculate A transpose by A. So A transpose is 1, 1, 2, 1, 0, 2, and then we multiply this by the matrix A. So we have 1, 2 plus 4 is 6, and then 1 plus 0 plus 4 is 5, 1 plus 0 plus 4 is 5, and 1 plus 0 plus 4 is 5. And then we can calculate A transpose B. So we have 1, 1, 2, 1, 0, 2 by B, which has components 2, 3, 1. So we have 2 plus 3 plus 2, which is 7. And 2 plus 0 plus 2 is 4. And therefore, using this equation, we can solve for X by inverting A transpose A, which is a simple 2 by 2 matrix. And from that, you'll be able to easily calculate the error to the approximation of B. If we have a P by Q matrix A, the linear system AX equals B has a unique least squares solution if the product of the transpose of A by A is invertible. So recall the normal system associated with this linear system was A transpose by A by X is equal to A transpose B. And therefore, if the inverse of this resulting matrix exists, then this least squares solution is unique. And also, if C is the column space of A, the projection of B onto the column space is obtained by multiplying the least squares solution by the matrix A. So recall that this was the approximation to the vector B. So therefore, if we solve this equation for X and then multiply by A, as we've done previously, we obtain X is the inverse of A transpose A by the transpose of A by B. And therefore the projection of B onto the column space of A is A multiplied by X. So we have the inverse of A transpose A by the transpose of A by B. So we've previously obtained this solution by solving this equation. So all we need to do to project B onto the column space of A is multiply this least squares solution by A. So we have A with the following components. Multiply by X. So that gives 3 minus 2.2. 3 plus 0. And 6 minus 4.4. And you can verify that this vector is in the column space of A by writing it as a linear combination of the column vectors of this matrix using these values in the least squares solution as the coefficients of the linear combination. So that's the case because remember that multiplying a matrix by a vector is the same as multiplying each entry of this vector by the corresponding column vector of this matrix. If S is a subspace of the real space of P tuples, then a linear transformation T from Rp to S, which maps every vector in Rp into its orthogonal projection in S. So effectively, the projection of V onto S can be written using the projection matrix that were derived for the least squares solution. So that was equal to A by the inverse of A transpose by A by the transpose of A. And we construct the matrix A using any basis for S as its column vectors. And for example, suppose we have the subspace S being the xy plane, and we have the following basis vectors for S. So we have 1, 0, 0, and the second basis vector has components 1, 2, 0. And we want to find the matrix that maps every vector B in 3 space to the subspace S. So what we do is assemble the basis vectors in the matrix A as columns of this matrix. So we have 1, 0, 0 and 1, 2, 0. And now we can compute this transformation matrix by computing this product. So if you evaluate this product, you're going to get T with components 1, 0, 0, 0, 1, 0, and 0, 0, 0. So for example, if you project this vector B on the subspace S, and B has components 1, 1, 1, then you just multiply T by B, which will give you the following vector. And this is the same result that we got when we derived the standard matrix for the orthogonal projection on the xy plane, as expected.